Okay, hello everyone. This video I'm going to show you the moment of inertial calculation in a composite areas. Okay, in previous video, we already show you the very basic of the moment of inertial calculation, and we use the rectangular as the example to show you the formula for the rectangular moment, the inertia formula for moment of inertia for rectangular, and also the parallel x theorem. Okay, and now we have to give more advanced situation because last video I just say in some case we not just only deal we might not only deal with very simple shape, and most of the time we are dealing with the composite areas, or you can just simply speak in more complicated cross section areas. Okay, but to deal with composite area, it's just very similar to what we did in the moment of centroid calculation. If we want to determine the centroid of a composite area, the strategy is just to decompose your complicated shape into a simpler shape like a rectangular or right triangle. Okay, and in the moment of inertial calculation, we have the same idea. We use the same idea. First of all, divide your area into a composite part, or simple parts. Okay, into simple parts. Okay, in the moment of area calculation, in this course, the simple means the rectangular. Okay, rectangular shape, because rectangular is the most simplest shape in the moment of inertial calculation. Yeah, of course, there's some circular area or half circular area or triangle shape, but in moment of inertial calculation, in this course, we just use a rectangular as our basic part. Okay, and then after you decompose your areas as a simple divide your area into a simple parts, and then try to locate their centroid. Okay, that's very important. Locate their centroid, and use the parallel axial theorem, and then add all the moment of inertia of simple area together, and then you will get the final moment of inertia of composite area. So simply speaking, just divided your area into many of simple shape, and then compute the moment of inertia of each simple shape or each simple area, and then add them together, and you get the composite moment of inertia. Okay, and during the calculation, you need to use the parallel axial theorem. Okay, because most of time there your simple area, your simple part doesn't rotate along with the centroidal axis. Okay, we'll use the one or two example to show this. Okay. Okay, so let's first example is the example 6.9 from the textbook. So you see this is a shape, okay, the cross-section area of the certain beam, okay. Okay, this cross-section area look like this. It's just I don't know how to describe this in English. It's in double L. This is the L. This is the L. I'm not sure. Double L, or say okay S. Okay, screw S. S, yeah, S shape. Maybe S shape. No, S shape. Okay, he said find the moment of inertia of this cross-section area, and he said about X centroidal axis and Y centroidal axis. And in this problem, okay, this X, just like this showed in this graph, this X is a centroidal axis. This Y is also centroidal axis. Why? Because this shape, the centroid, is just right at the C. Okay, so we set up the coordinate based on at this C point. So this is centroidal axis X. This is a centroidal axis Y. Okay, in this problem is very in this problem you don't have to calculate centroidal axis at the very beginning. That's good. We save some time because in later Later in the moment, bending moment calculation. Sorry, the stress calculation in the bending beam. You need to calculate the so-called neutral axis by yourself. Okay, but in this problem, okay, the centroidal axis is already tell you, so you don't have to calculate it. Okay, but we will go to the neutral axis calculation later. Okay. Okay, so it just tell you just this problem just want to calculate moment of inertia with respect to x axis and y axis. Okay, so we okay, so let's write some formula for you for moment of area. Let's see. Okay, if you okay if you rotate along this axis and you rotate along this axis, okay, so this is your B, this is your H, so this will be your B, this is your H, so it's 1 over 12 B H cubic. Okay, that's just the take a make a note here. So that's the okay, you see these two is different. Okay, it's all based on your what's the real rotational axis. Okay, okay, rotation is horizontal, and this is your B, and this is your height. If rotational axis is vertical, sorry, is a vertical. So this is your B, and this is your H. This is your height. So it's different. Be careful. Be careful. Be careful. So this H. Okay. Okay, so this area, is not a simple rectangular shape. Okay, so how do we calculate moment of inertia of this shape? Yep, just like we just mentioned in the last slide, we have to divided our complication into a simple shape. Okay, maybe I didn't write very well. So I didn't draw it very well. Okay, let me redraw it again. I don't know. Okay, so let me put the geometry information in there. So he said I should use the black. Say this is 100, so I believe this is also 100 because I think this has a symmetry. So this is 100 here. This is also 100. So okay, here is 600. And what else? So he say, okay, here is 400. Okay, it's units, millimeter. Be careful. Okay, so we can start the calculation. Okay, so the first of all, you have to divide your system into a simple area. Okay, so simple in this course, especially for the moment of inertial calculation, just divide into a lot of rectangular shape. And you have many ways to divide it. So I choose this way. And I think that if you have the textbook, okay, the textbook use the other cut in other fashion. Okay, the textbook, I think the textbook use this. Okay, maybe I erase this a little bit. In the textbook, it use this. In textbook, it cut like this. This is from textbook. Textbook cut in this fashion, okay, and calculate the moment of inertia with respect to x and y. But I intentionally use this. I intentionally cut this. I intentionally cut in this fashion. Okay. I just want to show you, no matter what fashion you choose, I cut in this way or that way in textbook, you will get the same answers. but okay, so I intentionally cut this way. Okay, and after you cut your divide your complex area into your simple area, so what's the next things to do? Okay, so okay, the next thing you just in previous slide we just say or determine your centroid. Okay, the centroid may be in this shape. Okay, be careful in this shape. The centroid maybe looks like maybe it's not in scale. I think centroid is here. In this shape, the middle one, the centroid is here. And the final one, I think the centroid is probably here. Okay, that's very important. Okay. And now we draw the rotational axis. Okay, here is the rotational axis for x. X is here. This is our maybe I use another shade. Maybe this is better. Okay, this is this is x. Okay, and here is y. Here is our y. Sorry, I cannot draw very well. Here's our y. Okay, maybe I need to use another color. This is x. This is y. Okay. Okay, so let's calculate ix first. Let's calculate ix first. Okay, so ix means to calculate moment of inertia with respect to x. Right now, our x is this axis. It's just centroidal axis. Okay, so okay, we have the left, middle, and right. Okay, we start from middle one first. Okay, middle one first. The middle is this area. Okay, because middle is here because I cut middle is here. Okay, middle. Okay, it's because this is this centroidal axis. It just passed through the centroid of the middle part. You see the centroid of the centroid of the middle part, just in the x axis just pass through the centroid of the middle part. Okay, so in the middle part we can use the formula for the moment for the rectangular moment of inertia for rectangular directly. Okay, because this is just pass through this axis, x axis just pass through it's the centroid of the middle part. So it's 1/12. Okay, and the BH3 square. Okay, be careful, rotational x axis is here. So what is our B? Okay, our B is here. So what's the length is here. Okay, so it's 600, it's 100. So of course here is also 100. So here is 400. So our is 400 times 10 to the power minus 3, and h squared. H is here. H is 100 millimeters. So 100 times 10 to the power minus 3, and B is 3 square cubic. So if you use your calculator, what is your answer? Okay, let me just use the calculator to calculate again. So it's 400 times 10 to the power minus 3, and times 100 times 100 times 100, and times 10 to the power minus 9. Okay, divided by 12. So it's about 3.3333 times the 10 to the power minus 5. Okay, this is for middle part. Okay, so for I just and what about the left hand side and right hand side? Okay, and right hand side and left hand side, they have the same shape and they have the same position. Okay, so they are the same, so we can calculate together. Okay, so let's focus on the left first. Left is this part. Okay, so you see this centroid is here. Okay, but the x-axis is here. So the x-axis is not passed through the centroid of the left part. the x-axis does not pass through the centroid of this part of the centroid of the left part. So you cannot only use this formula directly. You have to use a parallel axis theorem. Okay, so but you still need to calculate the use the moment of inertia formula for rectangulars to calculate this. Okay, calculate moment of inertia with respect to its centroid first. So 1/2. Okay, the centroid, the rotational axis here. So here is your B. Okay, what's here? B is 100 millimeter times 10 to the power minus 3, and here is your H. So what's the H here? I think H here is 400. Okay, so it's 400 times 10 to the power minus 3 and square. So, but this is the moment of inertia when the left part rotate along its centroidal axis. But right now this part is not rotate along his centroidal axis. He rotates along this x-axis. So you have to use a parallel axis theorem. So you need to add AD squared. A is the area of this part. So this is 100 times 10 to the power minus 3, and here is 400 times 10 to the power minus 3. Okay, this is A. Okay, this is just your area A, and you have to add a D squared. So what's your D? D is a distance between your centroid to your rotational axis. Okay, so here is the centroid of left part. So the D is here. D is here. Okay, so what is D? What's the distance D? Okay, because right now we are calculating rotation axis. Our rotational axis is here, so we need to know the distance between this rotational axis and the centroid of the left part. Okay, so what's the distance here? Here, it needs a little trick, because here is I think because this is symmetric, so here is 50, right? Okay, so let me see. Okay, so what's with this just here? So this is 200. This is 200. Where's this is 50? Oh, okay, I see. So, okay, here is 200. Okay, because it's at the centroid. Here is 200, and we need to add sorry, we don't have to know that. We don't need to know the distance here. Sorry, my bad. Okay, let's focus on this distance. What's the distance here? Okay, let's see. This is, I think this is because this here is 50. Here is 50, but what is distance between? Okay, so here I think it's also 100. AD square. Let me check. AD square 150. 50, 200. Yeah, it's kind of very strange. Yeah, what's the distance here? So here is 100. So what's distance here? So okay, here is 300. Okay, here is 300. So here is 300. Okay, so here is 200. So this is 200. So here is 100. 100. Anyone agree with this? 100 millimeter. Is that true? 100 millimeter. Really? 100 millimeter? Okay, so here is 100. So this here is 50. 50. Okay, so here is 200. So here is 200. 200 is here. So this is 100 here. Here is 100. And it's divided by, okay. Okay, so here is 150. Oh my God. 150. Okay, so 100. So this is, so here is 50 because it's symmetric. So here is 50. Here is 50. Okay, so it's 100 plus 50. So your D is 150 millimeter. 150 millimeter and the square. Oh, okay. It's okay. So this is just the left part. So let's see what's its value. Oh my God. Hope I'm calculating right. 100 times 100 times 10 to the power minus 3. And times 400 times 400 times 400. Yep. Times 400 minus 9 divided by 12. So it's 5.3333 times 10 to the power minus 4 and plus AD squared. Okay, so 100 times 10 to the power minus 3. And A times 400 times 10 to the power minus 3. And D squared, so 150 times 10 to the power minus 6. So 9 times 10 to the power minus 10. So what's 5.3333 times 10 to the power minus 4? So it's 1.43333 times 10 to the power minus 3. And we only calculate left and right hand side is the same value. The right part is the same because symmetry. So we have to times 2. So left plus right will be 2.8666 10 to the power minus 3. So we add this, the middle part and left and right together. So what the final value is 5.3333 times 10 to the power minus 5. So our answer will be 2.89999 times 10 to the power minus 3. So it's very close to the first answer. Yeah, our answer is a meter power 4. Okay, so be careful. Okay, so the problem here is not only you need to identify the geometry information very carefully. The thing I just stuck with is to determine the distance between the centroid and the rotational axis. I think my answer is right here is 200. And and here is 300. So here is 300 and here is 200, so this 100 and this is 50, so 150. Yeah, determine the geometry information very careful. Okay, because the problem won't tell you, you have to identify by yourself. Okay, so this is the first part. We just calculate the centroid with respect to x-axis, and we have another part calculate the y-axis moment of inertia with respect to y-axis. Yeah, but this video is kind of too long, so we just calculate the other answer in the next video. Okay, here is the first video. Okay, so we'll see you in next video. Next video, I'll calculate the remaining part of this problem. Oh, you have to be careful. Okay, see you in the next video. Okay, bye-bye. Oh, okay.